Guys, let's look at how we do a two-sided significance test. And I suppose we need to take some time and explain what we mean by a two-sided significance test. So it would help us to have a context. So here is today's context. Skittles. All right. So, guys, there are 5 Skittle colors in an original bag of Skittles: green, red, yellow, purple, and orange. There are 5 of them. So the question is this: if you look at the population of all Skittles that are produced, because there are 5 different colors, does that mean that 100 divided by 5, or 20% of Skittles are each color? So in other words, in the population of Skittles produced, is it that 20% of them are green, 20% are red, 20% are yellow, 20% are purple, and 20% are orange? So now understand, I mean in the population, is it 20%? In an individual bag, I assume that when they make Skittles, there's a giant vat of Skittles and they all get mixed up and then they are mechanically processed into bags. I assume there isn't a Skittle minion somewhere that's putting a very specific number of red and green and yellow and purple and orange ones into each bag. They're filled mechanically. So, can we use a random sample in order to get some idea of what the population parameters look like? So, I've already opened this bag of Skittles. What's sad is I've also gone through and I've already organized them all by color. So, here are the orange Skittles. There were 90 orange ones. Yellow, 88 yellow Skittles. Purple, there were 87 purple Skittles. Green, there are 80 green. And then red, 69 red. So the truth is, we got fewer red than any of the other colors. So are we getting, is it that in general they make fewer reds, or is it that maybe this bag just happens to have fewer reds just by random chance alone? So the question today is this. Ooh, taste the rainbow. Look, we can lay them all out like this. So in the population of Skittles that are produced, are they essentially making 20% of every color and then just putting them in a big vat and mechanically putting them into bags? Or can we find evidence that maybe one of the colors is different from 20%? For some reason, students tend to favor the red ones year after year. So before we opened that bag, I didn't know if I should expect more red than 20% or maybe less red than 20%. So the truth is, maybe the Skittles company thinks people really like reds, and so maybe they're really putting more red in the bags to make people happy. Or maybe if they know that people really like red, maybe they're purposely putting fewer red into the bags, which means that you have to buy more bags in order to get more red Skittles. Who knows? So the null hypothesis, though, is simply going to be that nothing special is going on, that they don't work that hard and they just make 20% of each color. The alternative hypothesis is going to be then, can we find evidence that maybe the proportion of red Skittles is different from that 20%? Before I opened the bag, I didn't know if I should give it a direction. In other words, I didn't know if it would be higher than 20% or lower than 20%. So all we're going to do is specify an alternative that says it's not 20%. So in honor of the red Skittles, I shall use a red pen. So today's question: is the proportion of red Skittles different from 20%? Okay, so let's define our population parameter. So the population proportion of red Skittles So the hypotheses, the null hypothesis, is always written as an equation. So if the company isn't working very hard, they're simply making 20% of each color, and we're not going to think too much about it. So the proportion of red Skittles, if nothing special is going on, maybe that proportion is just 0.2. We're looking for evidence that maybe that proportion is different from 0.2. Maybe it's higher, maybe it's lower. The reason that this is called a two-sided test is instead of using an inequality which favors one side, a greater than or a less than, we are going to use a not equal to alternative. And a not equal alternative is used when we see the word different. We are looking for evidence that the proportion of red is different from 20%, not greater than or less than. I'm looking for evidence of a difference. So in terms of my conditions, randomness. So I have to believe that there isn't a Skittles minion that's specifically putting a given number of green and red and yellow and purple and orange Skittles into each bag. I assume that the Skittles are put into a giant vat, they're mixed up, and then they are put into bags mechanically. So we can't really act like this is an SRS. It's certainly not that. So we have to act as though our bag of Skittles is a random sample. I have no reason to believe that it's not random. I have no reason to believe that there's a little Skittles minion putting a specific number of each color in the bag. So, in terms of independence, there were a total of 414 Skittles in the bag. So I'll use the 10% rule. So 10 times 414 is 4,140, and that's certainly less than or equal to the number of Skittles in the population. Number of Skittles produced. So in terms of normality then, I should use the null hypothesis value. We're going to assume, the p-value assumes that the null hypothesis is true. So we have to act as though this is our true population parameter. So we're going to take n, which is 414. That was the number of Skittles that we had. N times 0.2. So 414 times 0.2. That value comes out to be 82.2. Well, that's certainly greater than or equal to 10. So that's the number of successes. And then the number of failures would be 414 times 1 minus 0.2, or 0.8. So the 414 times 0.8, that gives us 331.2. That's also greater than or equal to 10, so our conditions are met. And now we'll calculate our sample statistic. So the p-hat, by actually looking at, I actually counted them, there are 69 red Skittles in the giant bag of Skittles out of a total of 414. So our p-hat is 69 out of 414. So I'm also going to write that as a percentage, if you will, or as a decimal, I suppose. So that's about 0.167. So it's not 20%, it's a little less than 20%. But the truth is, even if the population parameter were really 20% of Skittles are red, if you're looking at a random sample, sometimes you'll get fewer, sometimes you'll get more than 20%. So we certainly got less than 20%, but is it low enough, is it different rather, enough from 20% for us to believe that the population proportion isn't 20%? So I'm going to call this 0.167. So understand then, a p-value assumes that the null hypothesis is true. It is a conditional probability. So, what is the probability that our sample proportion of red Skittles is as or more extreme than 0.167? So what is the probability that our sample proportion of red Skittles is as or more extreme than 0.167 under the condition that the real population parameter, the proportion of red Skittles, is really 20%? Again, it's a conditional probability. We are assuming that the null hypothesis is true. So it might be easier to describe what we mean by as or more extreme if we convert our sample statistic into a z-score. Okay, so our z-score here, our sample statistic is 0.167. So in the sampling distribution, if we're assuming this is the real population parameter, that is the mean of the sampling distribution. And then the standard deviation of the sampling distribution, that can be found by taking p times 1 minus p, so that's 0.2 times 0.8, and dividing by our sample size of 414. So I'm going to put that all into my calculator in one shot, and I'm going to make a z-score out of it. So my numerator is the 0.167. I'm going to subtract the 0.2. And then I'm going to divide by the 0.2 times 0.8. And I'm going to divide by the 414. So I get negative 1.68, if you will, for my z-score. So that z-score is also known as the test statistic. And we'll see just in a second. We'll see in a second that you can use the calculator to get that. But what I want you to understand is what we mean by as or more extreme. So this z-score means that our p hat is really 1.68 standard deviations. That negative sign means that we're below the mean of 0.2. So as or more extreme means we could be below the truth of 0.2, or we could be above it. So an equally extreme score would also be at least 1.68 standard deviations above 0.2. So the truth is that to calculate this p-value, as or more extreme means I need to include the likelihood of having a z-score that's as or more extreme than 1.68, so a z-score that's greater than or equal to 1.68, but I also need to include z-scores that are at negative 1.68 or below. So that's what we mean by as or more extreme. We mean at least 1.68 standard deviations away from the mean, or maybe even farther than that. So you could be 1.68 standard deviations below the mean or above the mean, or you could be greater than or less than that positive and negative 1.68. So because the normal distribution is symmetric, I don't have to calculate those two z-scores separately. So notice if I wanted to draw a little picture of it, I'm sorry, I didn't leave a lot of room for this. So z-scores have a mean of 0, the z-scores have a standard deviation of 1. So look, if you had a z-score of 1.68 and a z-score of negative 1.68, what we're really trying to find here is the likelihood of being greater than that, 1.68, or less than the negative 1.68. So we could use the normal CDF command, I suppose, twice to get both of those areas, but that's kind of silly because the distribution is perfectly symmetric. So we really only need to calculate one of those areas and then just double that value. So it doesn't matter which one you choose, so I just chose the positive one. So let's take the probability of a z-score that's greater than or equal to 1.68 and we'll just double that in order to get our p-value. Again, you're not going to have to work this hard. We're going to use the calculator to find the test statistic, and what we're about to calculate here is the p-value. You can always use your calculator to do that, but if you are using your calculator, the work that you need to show, you need to write down the name of the test that you are using. So you are doing a 1 proportion z-test. I'll come back and write that down in a second. Let's finish this. So if I wanted to do this by hand, I could take the normal CDF command. I could use the 1.68 as my lower boundary, and I could use 10 as the upper boundary. So, but understand, that's not the p-value. All I calculated was this, the probability that my z-square is greater than or equal to 1.68. I need to double that because this is a two-sided test. So the actual p-value, we'll call it 0.093. So we're going to confirm this test statistic by using the calculator command, this p-value by using the calculator command. The work that you would need to show then, if you were doing this, if you will, on the AP exam, you wouldn't have to show all of this work. All you would need to say is that you are using a 1 proportion z-test. 1 proportion. So our hypotheses are written with only 1 proportion, and we're using z-scores. So this is a z-test. So let's use that calculator command to confirm all of the work that we've done. So if you press the stat button, and you go to tests, and you go down to 1 proportion z-test, we need to enter then the null hypothesis value. That's why there's a little sub-zero here. Our null hypothesis value is 0.2. So X is the number of successes. Remember, our sample statistic was 69 successes, 69 red Skittles out of 414. So X is 69, N is 414. And this is a two-sided alternative, so you should choose the not equal to alternative here. That's where you're specifying your alternative hypothesis. And then if you highlight calculate, you'll see we get a slightly different answer. That's only because the calculator used a p-hat, a sample statistic of 0.16 repeating. We used 0.167, but it's not going to change our conclusion. The p-value is, again, about 9%, just like we already calculated. It would be perfectly fine to do all of this using your calculator. I want you to do that. So let's write our conclusion. So the first thing, we use our level of significance, or alpha. We compare our p-value to that. So notice, since our p-value of 0.093 is greater than the level of significance of 5%, this is not an unlikely outcome. So since our p-value is greater than our level of significance, we do not reject the null hypothesis. So this means we do not have evidence of the alternative. And look, you can just copy the words. We do not have evidence that the proportion of red Skittles is different from 20%. You can literally copy the words when you write your conclusion. We do not have evidence that the proportion, the true proportion, the population proportion of red Skittles is different from 20%. So What I want you to see is that there is a correspondence between, in other words, there's a relationship between a significance test and a confidence interval. Let's calculate the confidence interval, the 95% confidence interval for the true population proportion of red Skittles. So we're not going to do it by hand. We did it by hand in our last unit. What I want you to see is you can build that confidence interval all on the calculator. Watch this. So if you go to stat and you go to tests, we are working with one proportion. So what you want to do is scroll down here until you get to what's called a one proportion z interval right there. One proportion z interval. I'm going to highlight that and press enter. And look, the calculator's pretty smart. It's already copied over my number of successes, my number of trials, and the confidence level that we want to use is the 95% level of confidence. If yours does not say 95%, you can just type in 0.95 there. Highlight calculate and press enter, and it'll build the confidence interval for you. So notice all of the conditions are the same. So we have a randomness, an independence, and a normality condition. So instead of showing all of the work for building the confidence interval, if you wanted to, you could simply say that you are building a one proportion z interval instead of a test and write it down. So the confidence interval that you get here is, we'll call it 0.131 and 0.203. So I'm going to write down that lower boundary of 0.131, and then my upper boundary was 0.203. So look, just to review, let's review. This is, I'll write out what this is. This is a one proportion, so I'll abbreviate it since I'm out of room, a one prop z interval. That's what we just calculated. Okay, so let's interpret it just like in the last unit. So we are 95% confident that the true, or the population proportion, I'll say the true proportion of red Skittles is between 0.131 and 0.203. Now here's how the test and the confidence interval relate. Look, my p-value was greater than my level of significance. This is not an unlikely outcome. So we do not reject the null hypothesis. So we do not have evidence that the proportion of red Skittles is different from 20%. Well, why don't we have evidence of a difference? Because look at the confidence interval. 0.2 is inside this confidence interval. 0.2 is one of the possible population proportions. It is one of the possibilities for the truth. The confidence interval is trying to capture the true proportion of red Skittles. So look, if we have not rejected the null hypothesis, if we don't have evidence that the proportion is different from 20%, that means that the true proportion of 20% should be somewhere inside of this confidence interval, and it is. And that's because the confidence interval and the level of significance, the confidence interval and the level of significance add up to a 100%. So if you are using a level of significance of 5%, that will correspond to a 95% level of confidence. So if you are doing a two-sided test. Remember, a confidence interval, if you will, for keeping it simple, it's essentially cutting off the lower and the upper portion of the sampling distribution to give you a range of possibilities for the truth, but it's cut off two sides. So understand, a two-sided test at the level of significance of 5%, that corresponds to a confidence interval at a confidence level of 95%. So the level of significance and the confidence level for these to correspond, they should add up to 100%. So to explain how the 95% confidence interval can be used to come to the same conclusion, well, look, why can't we reject the 0.2? Why can't we reject the null hypothesis? Because the 0.2 is inside of that confidence interval. I don't have evidence against the 0.2. I don't have evidence of a difference from 0.2 because 0.2 is inside the 95% confidence interval. 0.2 is captured within the 95% confidence interval. So let's practice calculator commands here just for a second, and let's wrap this up. Let's say instead, let's actually change the conclusion. So understand, confidence intervals correspond to two-sided significance test. So let's change the level of significance. Do you see how the p-value is 9%? Let's change the level of significance from 5%. Let's use the 10% level. If we use the 10% level, look at what's happened. Now the p-value would be less than 0.1. It would be less than 10%. This would be an unlikely outcome if our level of significance is 10%, because what we're saying is unlikely values have to be lower than this. Well, if it is unlikely, then now all of the statements become positive. We do reject the null hypothesis. So we do have evidence that the true proportion of red Skittles is different from 20%. So can we reject the null hypothesis at the 10% level? You bet. Because that p-value is less than 10%. But the corresponding confidence interval is going to show us that. Look, the 10% level, using that as alpha, if I take 10% away from 100%, that leaves 90%. So the corresponding confidence interval should be at the 90% level. So let's use the calculator to build that. So if I go to Stat, Tests, and I want to build a 1 proportion Z interval, right there, make sure it says 1 proportion Z interval. We're working with proportions. I'll press enter. I'm going to use the same number of successes of 69. I'm going to use the same sample size, but I'm going to change the level of confidence to 90%. Well, notice what happens. Now the confidence interval is from 0.137. That's the lower boundary, and the upper boundary is 0.197. There you go, I wrote them down. So now the lower boundary is 0.137, the upper boundary is 0.197. Notice, at the 10% level, 0.09 is less than 10%, so we can reject the null hypothesis. We can reject this 0.2. We have evidence the real proportion of red is different from 20%. Well, the reason that the confidence interval matches that is, look, an alpha level of 10%. If we look at the 90% confidence interval, look at what's not in the interval. The null hypothesis value of 0.2 isn't in the interval. It's not in the interval. That's why we can reject that point 2. This interval suggests then that we have evidence that the real proportion is different from point 2, the real proportion of red Skittles. This yields the same result because we rejected the point 2. The point 2 is not captured. It is not captured. It's not in the 90% confidence interval. So I'm sorry that this lesson is a little bit longer, but I wanted you to see how confidence intervals and two-sided tests correspond. I wanted you to see the work one last time. I wanted to review, how do we interpret confidence intervals? How do we interpret significance tests? And most importantly, I wanted to make sure that we saw one more time how you can use your calculator, not just to find the test statistic and the p-value, but you can even use your calculator to build confidence intervals so that we can spend our time focusing on the interpretation.